Wait, we're on? Well, hello there. Today we're here to talk to you about Chapter 10, Lesson 7 of the Algebra 1 textbook. The objective of this video is to find the probability of independent and dependent events. But wait, what are independent and dependent events?
I don't know. Do you know what an independent event is, Esther? Why, yes, I do. An event is independent if the occurrence of one event does not affect the probability of the other. But do you know what a dependent event is, Ali?
Indeed I do, Esther. Indeed I do. Events are dependent if the occurrence of one event does affect the probability of the other.
Gee, thanks, Ali.
Oh, no prob.
But I'm still a tad bit confused. How do you classify events as independent or dependent?
Well, Esther, since you asked, I will explain how to do that. Say you toss two coins and they both land heads up. The result of tossing the first coin doesn't affect the result of tossing the second coin, so the events are independent. When trying to classify events as independent or dependent, ask yourself the question, does the result of the first event affect the result of the second event? It's simple. If the answer is yes, the events are dependent, and if the answer is no, the events are independent. Here's another example. You choose two cards from a deck without replacement. There are fewer cards for you to choose from the second time, so the events are dependent. And that's pretty much all you need to know for how to classify events as independent or dependent. Suppose an experiment involves tossing two fair coins. Sample space outcomes is shown in the tree diagram above. Determine the theoretical probability of both coins landing heads up. There are four possible outcomes in the sample space. Heads heads, heads tails, tails heads, and tails tails. Only one outcome includes both coins landing heads up. The theoretical probability of both coins landing heads up is 1/4. Now look back at the separate theoretical probabilities of each coin landing heads up. The theoretical probability in each case is 1/2. The product of these two probabilities is 1/4. The same probability is shown in the tree diagram. To determine the probability of the two independent events, multiply the probabilities of the two events. If A and B are independent events, then the probability of A and B equals the probability of A times the probability of B. But how do you apply these formulas in real-life situations?
I will explain that. Here's a real-life example. An experiment consists of randomly selecting a marble from a bag, replacing it, and then selecting another marble. The bag contains 5 purple and 4 orange marbles. What is the probability of selecting a purple marble and then an orange marble? As you see here, there are 5 purple marbles and 4 orange marbles and 9 marbles in total. To find the probability of these two independent events, you multiply the probability of picking out a purple marble and the probability of picking out an orange marble, and the probability of these two events is 20/81. Because the first marble is replaced after it is selected, the sample space for each selection is the same. The events are independent.
Oh, now I get it, but how do you find the probability of dependent events?
Well, you see, Ali. Suppose an experiment involves drawing marbles from a bag. Determine the theoretical probability of drawing a purple marble, then drawing a second purple marble without replacing the first one. The sample space for the second draw is not the same as the sample space for the first draw. There are fewer marbles in the bag for the second draw. This means that the events are dependent. The probability of drawing a purple marble on the first draw is 4/7. The probability of drawing a purple marble on the second draw is 1/2.
The probability of dependent events. If A and B are dependent events, then the probability of A and B is equal to the
probability of A times the probability of B after A.
Here's an example.
There are 4 red flowers and 8 pink flowers in a bunch. Sarah selects a flower at random, and then Maria selects a flower at random from the remaining flowers. What is the probability that Sarah selects a red flower and Maria selects a pink flower?
Sarah can choose from 4 red and 8 pink flowers, which is 12 in total. And Maria can choose from 3 red and 8 pink flowers, which is 11 in total. After Sarah selects a flower, the sample space changes, so the events are dependent. To find the probability of these two dependent events, you multiply the probability of picking a red flower, 1/3, times the probability of picking a pink flower after Sarah picks a red flower, 8/11. 1/3 times 8/11 equals 8/33, which is the probability of these two dependent events.
Stay classy, never trashy,
And always a little bit sad.